Let's now return to the three cases we identified earlier and treat each of them in turn. First, the overdamped case, where gamma on 2 is larger than omega naught. So here's our equation, here's our expression for x, and alpha 1, alpha 2 are now both going to be real. And they'll both be negative as well, because whatever is under this square root will be some number which has a lower absolute value than gamma on 2, and so alpha 1, alpha 2 must always be negative because of the negative gamma on 2 out the front. So that means that alpha 1, alpha 2 will give us sum of two decaying exponentials. So here's an example with some value for gamma, omega naught, and initial conditions that gives us sum of two decaying exponentials. So x here rises and then will slowly decay out as time goes to infinity. X will decay back down to 0. Not particularly exciting. The underdamped case is more exciting, however. In this case, alpha 1 and alpha 2 will be complex, and we can write that then as some real part and some imaginary part. So switching the order of this negative sign here and pulling out a factor of I. We'll write the imaginary part here as omega dashed, and the real part we can express in terms of some decay time tau, which is going to be 2 on gamma. So that allows us to simplify alpha 1, 2 and write it down like this. That just saves a bit of time when you're writing this thing down. So the total solution then will be some linear combination of the part with alpha 1 with a plus I omega t and the part with alpha 2 with a negative I omega dash t. We can take out a factor of the negative exponential. What we have then is a negative exponential multiplying a solution that looks like the solution we had to the undamped case, except that where previously this frequency was given by root k on m, which is in fact now omega naught, the frequency now is omega dashed, which is slightly lower. This is a decaying oscillation because of this decaying exponential. So in this example, we have a gamma of 4, an omega naught of about 20, a little higher. I've organized it here so that when we find omega dashed, it gives us exactly 20, and our solution falls under this envelope of this decaying exponential that decays as e to the negative 2t. Thirdly, we'll consider the case of critical damping, where gamma on 2 is exactly equal to omega naught. So now our solution for x looks like this, and alpha 1, 2, well, the bit under the square root here is equal to 0, so alpha 1 is equal to alpha 2, which is equal to gamma on 2. So substituting that into our expression for x of t here, then x of t is equal to some constant, c1 plus c2, which is a single constant, multiplied by e to the negative gamma on 2 times t. This is a single function, but we know that for a second order equation we need two linearly independent functions we can add together and solve for our two initial conditions, initial position and initial velocity. So this isn't enough. We've got a problem, and we need to find a second independent solution. We'll try a function that looks like this. Here's the bit that we found before with the exponential damping of gamma on 2, and we'll try an added solution of t times e to the negative gamma on 2 times t. So this is the bit that we're adding. What we want to do is show that this function of x can solve our differential equation in the case where gamma on 2 is equal to omega naught. To do that, we need to know x of t, x dot, and x double dot, and we'll substitute x dot, and x double dot into our equation, our differential equation. But in the case where gamma on 2 is equal to omega naught, we can write it like this, so we get rid of omega naught squared. And substitute in these expressions for x dot, and x double dot, and show that it equals to 0. Well, it's kind of laborious, but here it is, and we can take out everything that has a common factor of c1, everything with a common factor of c2. All of this cancels, and all of this cancels, and so it's true. 0 equals 0, and this function of x solves the differential equation for the case of critical damping. What does critical damping look like? Well, here's our function for x, and we'll take an example with some value of gamma and some initial conditions. So what critical damping does, in fact, is it returns to equilibrium the fastest. So compared to an overdamped case or an underdamped case, the critically damped case will not oscillate, but it will also be the fastest return to equilibrium. And that's useful if you're designing something like car suspension, for example, where you want the suspension to react quickly, so you don't want it to be too damped, so you don't want it to be sort of slowly returning to equilibrium, but you also don't want a car to oscillate.